Really big idea in calculus that they love to ask you questions about is the continuity of a function. All right, the continuity of a function. So we've already kind of talked about a lot of the stuff that we need to determine continuity, but we're going to put it all together. So let's start with the simple definition. The simple definition of a function being continuous on an open interval is if its graph can be drawn without a pencil without lifting the pencil from the paper. So I'm going to give you a minute, and I want you to graph each of the following functions on the interval. So for example, with this first one, x squared plus 1, and this is interval notation right here. Okay, this is interval notation. If you're not familiar with it, what it's telling you is that the x minimum value is -3 and the x maximum value is +3. Okay, so if you're trying to graph it on that interval in your calculator, you need to type in the function x squared plus 1 and your y equals, and change your x minimum to -3 and your x maximum to +3. Don't worry about adjusting the y values. And based on those graphs, I want you to say which functions you think would be continuous on the interval, and tell me whether you think you can trust the graphical results. So I'll show you all the functions here. Here are the 4 functions I want you to graph. X squared plus 1, 1 over x minus 2, sine of x over x, and x squared minus 4 over x plus 2. I want you to graph those individually, determine whether you think that they are continuous on those intervals, and whether or not you know that there's an issue. So pause the video, graph those in your calculator, write down those results in your notes, and then come back to the video and I'll share my results. So A here, y equals x squared plus 1, is a parabola. It's a quadratic function. Quadratic functions are polynomial functions. Polynomial functions have a domain of all real numbers, so it is continuous everywhere. Okay, this function is continuous everywhere. There are no issues, no holes, no asymptotes, no problems whatsoever. Example B, y equals 1 over x minus 2 from -3 to 3. Hopefully it's pretty obvious to you that there's a vertical asymptote at x equals 2. You probably need to go and brush up on those rules on holes and vertical asymptotes and horizontal asymptotes from pre-calc if you don't remember, because they're very, very important, especially when we're talking about continuity. So this is continuous everywhere except for x equals 2. That's the only place where we have an issue. Everywhere else, it's continuous. There are no issues there in the domain. C, y equals the sine of x over x from -pi to pi. Now, here's one that's very deceiving. It looks, if you just look at the graph, it looks completely continuous. It looks like there aren't any issues, but we've already talked about this function a little bit. It has an issue at 0. When we plug in 0 into this function, we get 0 over 0, which causes us to have a hole. So remember, holes really don't show up on our graphs. You can't always trust the graph. You've got to be aware of, usually the denominators are a good indicator of where you're going to have a discontinuity. You can't divide by 0, so if the denominator ever equals 0, then you're going to have a problem. Now D is another example. You graph it, it's not going to look like there are any issues. X squared minus 4 over x plus 2 from -3 to 3, it doesn't look like it has any problems. And when you graph it, it actually looks like a straight line, which you're probably not expecting, because looking at that, it's a rational function. You expect rational functions to have multiple curves, but this one doesn't. It graphs as a straight line. Go back to pre-calc for a second. Let's think about y. If we factor that numerator, it's x plus 2 times x minus 2. And the denominator is x plus 2. We can cancel out those x plus 2's. So the simplified version here, x minus 2, is what the function looks like. that's what the function behaves. It behaves like the line x minus 2, but there is a hole at -2 because that's the factor that we canceled out. So this one is also continuous everywhere except for its hole at x equals -2. Now, something that's going to come up later, so we might as well talk about it now, is, well, where should the y value be at that hole? What value would plug in the hole? After you figure out where it's at, you plug it into the simplified version. So -2 minus 2 is -4. So the hole is at the point -2, -4. -4 is the y value that's missing. Like I said, that will come up again later, so you want to kind of keep that in the back of your mind, okay? Now, let's look at the calculus definition of continuity. You've got to know this definition. You've got to know the three parts, because if you are asked on a quiz or something like that to explain whether a function is continuous, you have to give these three reasons. Okay, so the three reasons are: f of c is defined. That means it has a value. So, for example, f of 2 equals 4. That means c is 2, it equals 4. Since it equals a number, it is defined. It exists, okay? Condition number 2, the limit as you approach c of f of x exists. Well, in order for that limit to exist, the one-sided limits have to equal the same thing. So you have to show testing the one-sided limits. And then the third condition, to be continuous, is that that two-sided limit has to equal the value of the function at that point. Okay? We talk about a function being continuous on an entire interval from a to b. A is your first x value, b is your second x value, if it's continuous at each point in the interval. That's kind of one of those duh statements, but it's in the textbook, so I'm going to share it with you anyways. And if your function is continuous everywhere from negative infinity to positive infinity, we call that everywhere continuous. Again, pretty obvious, but just wanted to state it. So here's an example of an AP question of the day, not really related to the continuity, but let's look at it anyways. We're told that the limit as x approaches 2 of f of x is 5, the limit as x approaches 2 of g of x is 6, and f of x is less than h of x, which is less than g of x for all x. Now, you should be thinking, when you see this right here, that should be making you think squeeze theorem. Okay, that should be making you think squeeze theorem. But remember, we've got to have very specific conditions for squeeze theorem. These two limits of f and g have to be what? The exact same value. Are they the exact same value? No, they're 5 and 6. So let's talk about which of the following statements must be true. I want you to pause the video for a second, and I want you to go through these three statements and see what you think about whether they're true or false, and then come back to the video and I will give my explanation. So statement number 1, f of 2 equals 5. That is not necessarily true. Just because the limit as we approach 2 is 5 does not mean the value of the function is 5. Anytime you're trying to figure out these true-false statements, try and come up with a situation where it's not true. Try and come up with a situation where it's false. So, for example, we could have a hole. Okay? We could have a hole. So let's say this is 5 right here and this is 2. Okay? We're approaching 5. But the actual value of the function is, we'll say it's 3. Okay? So statement number 1 does not have to be true. Usually it is, but it doesn't have to be. All right, let's look at number 2. G of x is less than or equal to 6 For all of x greater than or equal to 2, the function, the y values, g of x, the y values of g are less than or equal to 6 for all of our x values greater than or equal to 2. There is no way that they've given us enough information to decide whether all of our y values from that point forward are less than or equal to 6. Not true. Statement number 3. 5 is less than or equal to the limit as x approaches 2 of h of x, which is less than or equal to 6. Now, this one probably makes logical sense, and they're trying to get you to think that it's squeeze theorem, but it's not. Squeeze theorem, they have to be the exact same values. You can't just say that the limit is between those two values because the limit may not exist. Okay, the limit may not exist at that point. So 3 is out as well. This is one of the situations where none of the statements must be true. They could be true in certain situations, but they don't have to be true all the time. Okay, must be true means all the time. Okay, let's get back to our concept of continuity. So we have two types of discontinuity, meaning it's not continuous at a point C. Now, we've talked about these in pre-calculus, but we're going to give them kind of calculus terms, so to speak. The first one is a removable discontinuity. A removable discontinuity means that the limit as you approach C exists, but it's not equal to the value of the function. So a removable discontinuity is what we call a hole. You're just removing one little point from the function. So your limit exists, but it's not equal to the limit as x approaches C of f of x does not equal f of C. So you've got that limit. You have the first two statements of being continuous, but it's the third one that's not true. Now, a non-removable discontinuity means that the limit does not exist. Your left-handed and right-handed limits are not equal. So we've got two cases. We've got asymptotes with rational functions, and then we've got what we call jump discontinuities. That's what we called them before now. Just refer to them as non-removable now. But to give you a visual, asymptotes and jump discontinuities come from piecewise functions. Like in the picture that I've drawn here, the left side is coming up and then it jumps to another y value and the right side continues. So those are what we call non-removable. It's not just a single point that would fix the discontinuity. It's a bigger problem than that. Okay, we also have something called an infinite discontinuity. An infinite discontinuity is a vertical asymptote. Okay, a vertical asymptote. When your function approaches positive or negative infinity as x approaches C from one or both sides, then C is called a vertical asymptote. Now, I bring that up. I know you know what a vertical asymptote is, but I bring that up because they like to do problems like we just did, that question of the day, where they use the limit notation, and you've got to recognize the limit notation is describing a vertical asymptote. So if you see the limit as x approaches 2 of f of x equals negative infinity, then x equals negative 2 is probably a vertical asymptote. Well, not probably, is a vertical asymptote. Wrong color. Okay, now, I abbreviate vertical asymptote with a V and an A. Please do not do that on any tests or on the final exam if it comes up. That's not standard mathematical notation. There will be some abbreviations that you can use that I will bring up along the way, but VA for vertical asymptote is not one of them. All right, so let's talk about the continuity of each of these functions here. The first function, f of x equals 1 over x. It's a rational function. We should be thinking holes and asymptotes. no whole because we can't factor and cancel anything, so the denominator set equal to 0, x equals 0 is a vertical asymptote, but let's put it in calculus terms. F of x is continuous everywhere except for infinite discontinuity at x equals 0. Okay, I'm trying to get you used to the vocabulary here. Let's look at B. G of x is equal to x squared minus 1 over x minus 1. Again, rational expression, or rational function. We should be thinking wholes and asymptotes. We can factor this one, so we need to do so to see if we have a whole or an asymptote. In this case, it is a whole. Okay, so I'm going to kind of abbreviate a little bit here. F of x is continuous everywhere except for removable discontinuity at x equals 1. Set what you canceled equal to 0 and, x minus 1 equals 0. So x equals 1 is your removable discontinuity. Okay, let's look at h. H of x is x plus 1 when x is less than 0 and x squared plus 1 when x is greater than 0. It's a piecewise function, so you should be thinking the issue is going to be where we change. So we need to check the left-handed and right-handed limits. So when we plug in 0 into the first piece, we get 0 plus 1, which is 1. When we plug 0 into the second piece, 0 squared plus 1 is 1. Those agree, and these two functions themselves are continuous functions. X plus 1, x squared plus 1, those are continuous. So, this is not f, and that was not f up there either. That was g. My bad, not paying attention to details. This is h. H of x is everywhere continuous. Okay, last example, y equals sine of x. Okay, sine of x trig function, we should be thinking, is there anywhere where the trig function does not have a value? Sine of x always has a value. It doesn't matter what angle you are talking about, sine of x always has a value. So y is everywhere continuous as well. Now, not all of our trig functions are. Sine and cosine are, but all the rest of them have some discontinuities, and we'll discuss where and why a little later on. All right, so let's talk about some functions you need to be familiar with. And you may want to pause the video along the way so you can write it down as I'm explaining. Number one, polynomial functions. They are continuous everywhere. They have a domain of all real numbers, so they are continuous everywhere. If it's a polynomial, you're good to go. Rational functions, I've been trying to mention it, okay? They do have a domain of all real numbers except for wholes and vertical asymptotes. Those are the problems. Those are what you should be looking out for. Radical functions, okay? Radical functions, square roots, cube roots, fourth roots. Okay, you've got two scenarios. If it's an even function, if it's an even root, square root, fourth root, what's under the root has to be greater than or equal to 0. You can't take a square root of a negative number without imaginary numbers, and we don't deal with imaginary numbers in calculus. That's complex analysis. That's a couple of courses down the road if you get that far. Okay, we only deal with real numbers. You don't have to worry about I in calculus. Okay. So even root, can't take the square root of a negative number, so what's under the root has to be greater than or equal to 0. That's going to determine your domain. That's going to determine where you're continuous. If it's an odd root, cube root, fifth root, anything like that, you're good to go. You can take the cube root of a negative number. You can take the cube root of a positive number. You can take the cube root of a decimal, of a whole number, whatever you want to take the cube root of. So odd radicals, continuous everywhere. All right, exponential functions. E to the x, 2 to the x, negative 5 to the x. Those are continuous everywhere. They have a domain of all real numbers. You can raise e to any power that you want to, and you're going to get a y value out. So continuous everywhere for exponential functions. Logarithmic functions, on the other hand, if you remember back to dealing with logarithms, you can't take the log of a negative number. You can't take the log of a negative number. So whatever's inside your logarithm, the example that I have here is logarithm of the natural logarithm of x. X has to be greater than 0. Not equal to, greater than. Can't take the log of 0 either. So x has to be greater than 0 in this case. If it's x squared, you're good to go. X squared is always greater than 0. Because any number squared is a positive number. Positive numbers are bigger than 0. So where you're continuous there will fluctuate some with logarithmic functions. But what's inside the logarithm is greater than 0 is your domain, and you're continuous everywhere on your domain. Okay, here's the trig functions. Sine and cosine, all real numbers. You're good. You're continuous everywhere. Tangent. Tangent is sine over cosine. So you would have an issue where cosine is equal to 0. Well, where is cosine equal to 0? Cosine is equal to 0 at pi over 2 and at 3 pi over 2. Pi over 2 and 3 pi over 2. So you may see it written like this. Okay? All real numbers except for pi over 2 plus pi k. That's going to get you all the multiples. Pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, so forth and so on. Trig functions go on for forever. It also gets the negative ones. Negative pi over 2, negative 3 pi over 2. K is an integer, so it goes from 0 on up, or it can be negative numbers as well. But what it's doing is it's producing all those values for which cosine is equal to 0. All right, so let's talk about the reciprocal functions. They don't come up as much. Sine, cosine, and tangent are the most frequent, but you will also see the other trig functions as well. Let's talk about cotangent first, since we were just talking about tangent. Cotangent is just the reciprocal of tangent, so it's cosine over sine. So it has a problem where sine is equal to 0, which is going to happen at pi, 2 pi, 3 pi, so forth and so on, negative pi, negative 2 pi. So you'll see it written all real numbers except for pi k. Cosecant is the reciprocal of sine, so it has the same issues that cotangent has. Secant is the reciprocal of cosine, so it has the same issues as tangent because it has cosine in the denominator. Okay, so you may need to brush up on that trig a little bit. You have to do it. You got to know that unit circle, or it's going to hurt you. Okay, so I want you to take a second in your notes, and I want you to write down, without looking at your other notes, what are the 3 conditions for continuity? And then look back at your notes and see if they match.